Hello, everybody, and thank you for being here, and thank you, Payman, for the introduction. So my talk is going to be about distributed key generation on blockchain for blockchain. This is a joint work with Jan Kamenish, Andrea, David, Manu, Timo, Gregory, and Dominic. So I want to thank them as well here. So 5-6 years ago, when I was working on multi-party computation for a large number of networks, usually the first question people ask me was, why so many people? Why thousands of nodes? Why not 3 or 4? And I had a lot of motivation slides to motivate people to work on decentralized system, but blockchain changed a lot of things. And one of them was the questions people ask me. So now usually the first question I receive is, can you scale it to more? So maybe we don't need this slide anymore, but I'd like to talk about a little bit about why decentralization is good. So we don't want to have a single trusted party, so instead we want to trust a group, so this way we can increase our trust setup, and it gives us better security, reliability, and performance. Examples are going to be secure multi-party computation, threshold cryptography, and threshold signature scheme. This talk is more about threshold signature schemes. So what is a threshold signature scheme? Let's define it. So informally, assume you have n parties, and they want to sign a message together. So they want to sign a message together in a way that if T of them are honest and sign a message, they can successfully sign the message and create a signature for the message. But if less than T of them are present, they cannot create such a signature. So they want to make sure that T parties are necessary and sufficient. So any threshold signature scheme typically have 3 protocols. The first protocol is key generation. In a key generation protocol, parties together, or one party for them, create a group output, or a group public key as an output. And also for each node that participates in the protocol, the protocol should output a secret key. So in a signing phase, each party signed a message with its own secret key, and then they output a signature. And in a verification phase, a verifier should be able to gather all the signatures from all the parties. If they don't send a signature, it can be an empty signature. And then using the group public key, he should be able to verify if the signature on the message is correct or not. And the output is 0 or 1, if it's correct signature or not a correct signature. So before talking about how we can solve this problem and how we can do the DKG for this problem, I want to talk about non-interactiveness, why non-interactiveness is important, because this talk is about distributed key generation, which is non-interactive. So by non-interactive, it means that we are going to have only one round in the protocol. And it's very important because generally you only create keys once, then everybody go home, they come back and start signing. They might sign multiple and multiple times. So then the dealers who were active during the generation of the keys and help people to agree on the keys, they might go home. They might not come all at the same time to be online all. You can have, for example, the first dealer come online, deal its secrets, and then the next dealer come online. So you don't need to have them all online at the same time and synchronize at the same time. Another interesting point for a scheme that is non-interactive is that most of the non-interactive protocols are at the same time can be publicly verifiable, which is another good property. Because later, if the nodes are not available anymore to do the verification, anybody in the network can do the verification. So that's the motivation why we are looking into a non-interactive DKG, not any DKG. So now let's talk about why threshold signature scheme. So threshold signature schemes has a lot of application. The first application was even before cryptographers thinking about cryptography. So the first application was for democracy. So we decided that instead of having only one person sign the bill, we choose a group, and if a threshold of this group or a fraction of them sign the bill, then we kind of assume this bill is passed. Later, the threshold signature scheme used for voting-based consensus protocols. This is a similar approach like voting. So instead of everybody trust only one person to help them reach agreement, they work together, and so they sign the block or the value they want together, and if a fraction of them or a threshold of them agree on the block, then they assume it's accepted and decided. So another nice, interesting application of threshold signature scheme is creating random numbers. So if this threshold signature scheme has uniqueness property, you can use it as a random beacon. So starting with one random value, the group can sign this random value. The signature is unique, and it is uniformly chosen from the group. So it's a good random value. It's unpredictable, and then you can sign that random value again, and it's unpredictable again. So you can have a chain of random values. And random beacons are a very useful tool in distributed computing in general. So now we know there are a lot of applications for threshold signature scheme. Let's try to create one. The first step to create a good threshold signature scheme is to do the distributed key generation. But before doing a distributed key generation, let's see how the keys is really used. So very trivial threshold signature scheme is that each party create its own secret key and public key and use a well-defined signature scheme, not a threshold one, to sign. So each party sign completely independently. And for the verification, if T of them has a valid signature on the message, you can consider it a valid signature as a group valid signature. So this is correct. This is the correct scheme, but it's not efficient. It's a very inefficient scheme. So why it is inefficient? Because in this scheme, group public key size is O of n, signature size is O of t, and verifier should verify O of t of the signatures. So we want a scheme that we can combine the signatures to make it shorter, and to make the verifier job easier, and also to make the messaging that should pass in the network smaller. So now let's do a little bit of background on how we can create such a scheme. So one way to do the distributing keys or sharing the keys is used secret sharing, because keys generally are secrets. So we can use a secret sharing method to create keys. Assume in a secret sharing scheme, we assume there is one secret that we want to share it among n parties, such that T of them are necessary and sufficient to reconstruct the secret. So here, it's very important that less than T people can gather together, but they cannot learn any information about the secret. So it has complete secrecy property. So the first secret sharing scheme is introduced by Shamir. Usually they call it Shamir secret sharing scheme. So in a Shamir secret sharing scheme is based on polynomials. So we love polynomials here. So if you have a polynomial of degree t minus 1, you can assume the f of 0 of the polynomial is your secret. And then you can create a random polynomial. You can choose all the coefficients of the polynomials randomly and create a random polynomial of degree t minus 1 over the field. Then, because t points are necessary and sufficient to reconstruct the polynomial, then essentially t points are necessary and sufficient to reconstruct the secret. And up to t point reveals no information about the secret since polynomial is undefined. So it has perfect secrecy. So secret sharing scheme is based on this idea of Shamir. So how we can do a secret sharing is that we we have a secret, we choose a random polynomial, and we choose points on this polynomial. And we send one point to each party on this polynomial. So one party has 1 point of the polynomial. Later on, in the reconstruction phase, the parties, T of them can gather together and reconstruct the polynomial and reconstruct the secret. So we say the secret sharing scheme has secrecy property because less than T shares carry no information. So if one of the parties is not honest, is dishonest, and like say his secret to everybody, it doesn't reveal anything about the actual secret. And we say it has correctness property. It means that T shares are sufficient to reconstruct the key. Now, can we go from secret sharing scheme to key generation scheme? Because we don't want just secret sharing, we need key generation. So we can assume that there is, so there is a way. So assume that there is a public key and an associated secret key for the group. Then we can share the secret key of the group this way. So now, let's say we have an oracle, and this oracle is trusted. Then he can create a public key and associated secret key for the group, and he can share the group secret key to the parties. Then this sharing happens once, and later on, people can gather together and sign multiple times. Okay, but oracles are not real, so there is no oracle in real world, and we cannot trust a single party to do this sharing phase for us. So because this is what we wanted to avoid. We want a decentralized system. So now we want to go from distributed key generation step by step. First, we have to make sure that we have multiple dealers, not just one dealer. And we have to make sure that each dealer cannot cheat. And so instead of using a secret sharing, we need a VSS or verifiable secret sharing scheme. And then we can assume the DKG is multiple instances of the VSS. Now we have multiple dealers, each dealer do a VSS. Now DKG is a multiple instance of the VSS scheme. So now let's start with only one dealer. So the dealer do the sharing. If he is not trusted because he is not an oracle, the share might not be on a polynomial. Then we cannot reconstruct the secret anymore, or we cannot sign with the incorrect shares. So what we should do, we should commit to the polynomial. So now if we want to commit to the polynomial, we have to agree on the commitment. All the nodes should agree on the commitment of the polynomials. Otherwise, it's not enough. So because all the nodes should agree on the commitment of the polynomial, how we can reach agreement? Agreement is a very, very difficult procedure. It needs consensus. But good thing is that we already know blockchain. Blockchain is a method of agreement. So we can use blockchain to agree on the commitment of the polynomial. So we can put the commitment of the polynomial on the blockchain. And since we want to use blockchain for everything, let's say we put the shares of the people also on the chain. But blockchain has no privacy, so we cannot really put the shares on the chain. So now we have to encrypt the shares and put them on the chain. So what we have? We have a polynomial. We have points on the polynomial. We encrypt the points with the secret key of the parties, and we commit to the polynomial. Now we put everything on the blockchain. Now still, it's not enough because the encryption and the commitment might be completely on different polynomials. So a dishonest dealer might commit to something, encrypt something else. So we have to have a proof that, okay, if I have an encrypted share, this share opens to a correct point on the committed polynomial. So, and we use a zero knowledge proof for that. So I hope it's not that difficult. Okay? Now, this is the scheme. This is what we use for VSS scheme as a VSS. So let's go over it again. So we have a secret. The dealer have a secret. He creates a polynomial. Then he commits to the polynomial by using a simple commitment. So he commits to the coefficient of the polynomial. Now, he has to encrypt the shares. The way that we decide to encrypt the shares, because later on we want to do a zero knowledge proof on them, is that we chunk the shares we chunk fi, which is a share, and use the exponential L-Gamma encryption for each chunk. Then our zero-knowledge proof can prove that if we decrypt the ciphertext, then the decryption is going to be a point on the committed polynomial. Okay. Now, until this point, I only talked about VSS, or verifiable secret sharing. I didn't talk about now how we can go from verifiable secret sharing to the DKG, which needs distributed, which is decentralized. So still, I have only one dealer, which is a single point of failure. If the dealer is dishonest, he can learn the secret, he can distribute non-random polynomials, or he can remain silent in the protocol. So the next step is how to have multiple dealers. So to have multiple dealers, we can repeat the same procedure for each dealer. Now we receive multiple shares, and then we can add the shares to each other. Since Shamir secret sharing has homomorphic property, the addition works here for us. Now let's see what is homomorphic property. So we have polynomials. If you have a polynomial and add it to another polynomial, the result is a polynomial of the same degree. So it's very simple. So if I have y is equal x plus x2 and add it to y is equal 2x plus x2, then I have y equal 3x plus 2x2. And it's still a polynomial, and it has the same properties that we want. And now, if I have a random polynomial and add it to a non-random polynomial, the result is a random polynomial. So why it is true is because nobody can guess what is my first random polynomial, so nobody can guess what is the output of the addition. So this way, now assume I have two dealers. The first dealer chooses secret 1 and he's honest. Now I have a second dealer and he chooses secret 2 and he's dishonest. Now I have public key 1 for the honest people and S1 for the honest people, public key 2 and S2 for the dishonest people. My group public key is going to be PK1 plus PK2. My secret key is going to be f of 0 on the first polynomial, f1 of 0 plus f2 of 0 on the second polynomial. And the secret key of each party is a corresponding point, is the addition of the corresponding point of the polynomials. So this way, now I can have multiple dealers. Now, if I have enough dealers, I can make sure that at least one of them is honest. I can make sure at least one of them create a correct polynomial, correct random polynomial, and then this way I can make sure that the public key and secret key is going to be random. And the small secret keys, the sharing keys, are also random. So are we there yet? So is this protocol secure? We don't know. So there is an attack on this protocol, which is usually called rushing adversary attack. And the attack makes the group public key to not be random. So what is the attack? Is that if I'm a bad dealer, if I'm an adversarial dealer, I can wait for all the parties to create their polynomials and their public keys, reveal their public keys. Then I choose my own public key. So I can really choose what is going to be the group public key because I'm the last person. So because of this rushing adversary attack, the resulting public key is not random. But maybe we still have a secure protocol. Why we think maybe we still have a secure protocol? Because this type of attacks happened on other DKG, not the non-interactive ones, but other DKGs before. So Gennaro et al. Proved that similar scheme, that is a discrete log-based DKG protocol, cannot produce a uniform public key. And they showed that this attack works on that specific scheme. But they also have a solution for that problem. So they solve the problem and create a new DKG protocol that is producing a correct random output. But the problem is that the new scheme is is not non-interactive. It has additional round. For them, maybe it wasn't matter because the original protocol has 3 rounds, and then it was 1 additional round. Maybe that doesn't matter. But for us, we are looking for a non-interactive protocol, so we cannot use their technique. But there is another interesting observation as well. They also observed that some of the discrete log-based protocols or crypto systems remain secure despite the non-random public keys. So maybe we can do the same thing here. So similarly, we investigate the BLS threshold signature scheme, and we understand and we observe that this specific threshold signature scheme that we use remains secure even when using a non-interactive DKG that creates a non-random public key. So in the presence of a random oracle model and CDHD oracles, but I'm ignoring them. So what is the proof? So the first time I created the proof, it uses security proof with functionalities and simulator and actual real protocols and a lot of math. And our engineers says, oh, it's a very, very complicated proof. We don't understand anything. So this is the proof intuition. I'm not going deep into the proof, but I think it has a very good intuition. How we can prove why it's not important that the public key is not random for BLS. So we are following the Generos et al. Proof. And so what we can do is that we can say that any threshold signature scheme, specifically here, our BLS threshold signature scheme, can be reduced to D instances of signature scheme, of a one-party signature scheme, not a group, not a threshold signature scheme, where D is the number of dealers. So if I have 20 dealers, it means that my threshold signature scheme is running a 20 simple signature scheme in parallel, D times. Now, to break a scheme, the adversary has to break all of these individual signature schemes. The adversary has to break all D of instances of them. But we know one of the dealers was honest, so based on the assumption, we assume that we have enough dealers that at least one of them is honest. Since at least one of them is honest, we know the adversary cannot break the signature scheme of that specific honest people. Since he cannot do that, as a result, he cannot break the security of the whole threshold signature scheme. So this is the intuition behind the proof. I'm ignoring the formal proof here. But we also implemented our scheme. So for the zero knowledge proof in the scheme, we had 3 options. So we first choose the bulletproof as a zero knowledge proof because we needed a simple range proof, and bulletproof is very good for that. So then this is the bandwidth and computation and communication cost of the bulletproof scheme if we use bulletproof. Then we use a different signature scheme other than El-Gamal for different encryption scheme other than El-Gamal for encrypting the shares on the chain. For the optimization, here the optimization is to decrease the bandwidth. Bandwidth is important for us. And then lastly, we use a snark as the proof. And this is the cost of the optimized bulletproof and the snark. So if these numbers is too magical for you, I have more concrete numbers, which help you understand what's the cost. So this is the cost per dealer per DKG. I like to thank Andrea. His picture is here. He ran all this on his laptop, which was a 4-core laptop. It was a very simple one. So the cost might show a little bit higher because of that. But for bulletproof, we had around 100 kilobytes of message size or bandwidth that is required. And the prover computation needs around 15 seconds. And the verifier computation is around 12 seconds. If we optimize it, remember I said we optimize for the bandwidth because bandwidth is very important. If we optimize it, we can have a 27 kilobyte for the bandwidth, but then the prover and verifier times is going to be much higher. So the prover time is going to be around half an hour, and the verifier time is around 30 minutes. So the prover time, maybe it's not that much important on DKG because you run DKG once, like for example, every week or so. You don't run DKG a lot, and then it can be completely offline. It can happen, the proof can happen offline because it's a non-interactive protocol. But the verifier time is very high for that optimization. So then we tested with snarks. And then the bandwidth is 32 for the snark. It's still small. The prover time is around an hour, which is large. But the verifier time is around 7 milliseconds. So I think that one is our best option for now. Still, it has a very long prover time. So for future, I encourage any researcher to work on this scheme and try to make it better, make it more practical, make it more efficient. And however, we only run it once a week, but still 1 hour is a long period of time. So thank you, everyone, for listening to me. And I like also to thank Definity's DKG team and also our engineers who help us to implement this scheme.
Okay, we have time for a couple of questions. Anyone wants to ask a question, let me know. Meanwhile, while people are coming, maybe I ask a question. You mentioned that you need to do range proofs. Can you say where exactly in the statement that you need to prove proving range just comes?
Yes, so you remember I said that we break the encryption into chunks and then prove this, the chunks, and then I have to prove each chunk is in a range because I break it into the chunks.
So if you intend to use snarks for zero-knowledge proofs, how do you deal with trusted setup? Is it only between participants? Like, how are you going to address this?
Yes, the dealer should do the trusted setup. It needs a trusted setup.
But I mean, like, whoever produces trusted setup can fake proofs.
It cannot fake it, but it's one of the drawbacks of the snark is that it needs trusted setup. You are right.
Thank you.
Thank you for the presentation. And
Sure.
My question was, like, do you need, is it a necessity to have like an absolute external dealer, or can the participants themselves be the dealer? Because as you mentioned, you need at least one honest dealer, and for the secret sharing, you can have like n minus k. So can the participant function themselves as a participant as well as a dealer who publishes a polynomial?
Yes, currently we choose a number of parties to participate as a dealer. But the difference is that because we have the parties to do the threshold signature and run a consensus later, the group should be a bigger size because for them we need honest majority, or at least 3 of them should be honest. But the dealers should be from a smaller group because we are in any trust model at that. Only one honest node is required for that specific.
Yeah, thank you. Thank you.
Okay, let's thank the speaker again. And